This version also removed some features that were considered as unused or unsafe and therefore beneficial for security. Struct or arrays that contain mappings were allowed to be used only in storage and not in memory. And the reason for this was mapping members within such struct or arrays in memory were silently skipped. And this, as you can imagine, would be error prone. The visibility of constructors, either public or external, is not needed anymore. That's another change that this version introduced. The virtual keyword is disallowed for library functions because libraries can never be inherited from, and therefore the library functions should not need to be virtual. Multiple events with the same name and parameter types in an inheritance hierarchy are disallowed, again to reduce confusion. The directive using A for B with respect to library functions and types affects only the contract it is specified in as of this version. Previously this was inherited, now it has to be repeated in all the derived contracts that require this feature. Shifts by sign types are disallowed as of this version. Until now, shifts by negative amounts were allowed, but they caused a revert at runtime. The ether denominations of Fini and Szabo were considered as rarely used and therefore were removed as of this version. The keyword var was also removed because this would until now parse but result in a type error. It just results in a parser error as of this version. Let's now move on to Solidity version 0.8.0, the latest of the breaking versions of Solidity. This version introduced several changes, several breaking changes. The biggest perhaps is the introduction of default checked arithmetic. This is the overflow and underflow arithmetic checks that are so commonly used in Solidity contracts to prevent the wrapping behavior that results in overflows and has resulted in several security vulnerabilities. And until this version, the best practice was to rely on the OpenZeppelin safe math libraries or their equivalents to make sure that there are runtime checks for overflows and underflows, and these never result in vulnerabilities. And this is so commonly used that Solidity version 0.8.0 introduced the concept of checked arithmetic by default. So all the arithmetic that happens with increment, decrements, multiplication and division is all checked by default. And this might come at a slight increase of gas cost, but it also increases the default security level significantly. And it also improves the readability of code because now one doesn't have to use or see the use of calls to the safe math libraries in the form of .add, .sub, and so on. And as an escape hatch where the developer knows for sure that certain arithmetic is safe from such underflows and overflows, Solidity provides the unchecked primitive that is allowed to be used on blocks of arithmetic expressions where this default underflow and overflow checks are not done by the Solidity compiler. ABI coder version v2 is activated by default as of this version. Doesn't have to be explicitly specified, but if the developer wants to fall back on the older v1 version, that has to be specified. Exponentiation is right associative as opposed to being left associative. That was the case. This is the common way to parse exponentiation operator in other languages, so this was fixed as of this version. the use of the revert opcode for failing requires versus the use of the invalid opcode for failing asserts and internal checks was removed as of this version. Both these now use the revert opcode, and static analysis tools are allowed to distinguish these two differing situations by noticing the use of the panic error in the case of failing asserts and internal checks. When storage byte arrays are accessed where the length is encoded incorrectly, a panic is raised. That's another change introduced. And finally, the byte type, which used to be an alias of bytes 1, has been removed as of this version. Solidity version 0.8.0 also introduced several restrictions. Explicit conversions of multiple types are disallowed. Recall that explicit conversions are where the user forces conversions between certain types without the compiler necessarily thinking those are safe from a type safety perspective. So these explicit conversions being disallowed may be considered as a good thing from a security perspective. Address literals now have the type address instead of address payable, and these have to be explicitly converted to address payable if required. The function call options for specifying the gas and ether value passed can only be provided once and not multiple times. The global functions log0, log1, all the way to log4 that may be used for specifying events or logs, these have been removed because they were low-level functions that were considered as largely unused by Solidity contracts. And if a developer wants to use them, they need to resort to inline assembly. Enum definitions now cannot contain more than 256 members. This makes it safer because the underlying type is always uint 8, so 8 bits. That allows only 256 members to be represented by that type. Declarations with name, this, super and underscore are disallowed. Transaction origin and message sender global variables now have the type address instead of address payable, and again require an explicit conversion where address payable is needed. The mutability of chain ID is now considered view instead of pure. So all these different types of restrictions were introduced in this version that have an impact on security. Let's now talk about 3 categories of security checks that are relevant to some of the Solidity aspects we have discussed in this module. The first category is that of zero address checks. Recall that Ethereum addresses are 20 bytes in length, and if those 20 bytes all happen to be zeros, which is referred to as a zero address, that is treated specially in Solidity contracts and also in the context of the EVM, because the private key for a zero address is unknown. So if ether or tokens are transferred to the zero address, then it is effectively the same as burning them or not being able to retrieve them in the future. Similarly, setting access control roles within the context of smart contracts to the zero address will also not work because transactions cannot be signed with the private key of the zero address because nobody knows the private key of this zero address. Therefore, zero addresses should be treated with a lot of extra care within smart contracts, and from a security perspective, zero address checks should be implemented for all address parameters, specifically for those that are user supplied in external or public functions. The second category of security checks is what is known as the transaction origin check. Again, recall that Ethereum has 2 types of accounts. externally owned accounts, EOA, and contract accounts. Transactions in Ethereum can only originate from externally owned accounts. So transaction.origin is really representative of the EOA address where the transaction originated from. So in situations where smart contracts would like to determine if the message sender was a contract or not, whether it was an EOA, then checking if the message sender is equal to transaction.origin is an effective way to do it. There are some nuances in the usage of this, but at a high level, this is a check that you may encounter in smart contracts and has security implications. The third category of checks are arithmetic checks. We have talked about the concept of overflows and underflows. Just to refresh, where arithmetic is used with the integers in Solidity, if the value of that integer variable exceeds the maximum that can be represented by that integer, or goes below the lowest value that can be represented by that integer type, then it results in what is known as wrapping, where the value overflows from the maximum integer value of that type and becomes 0, or underflows below the lowest value representable, which is typically 0, and becomes equal to the maximum value representable by that integer type. And this, as you can imagine, can have big security implications because the values of those variables, maybe it's representing the balance of that account or something else within the context of the application logic, now wraps around and becomes either 0 or the maximum value, which can totally change the application logic that is working with such variables. So such overflows or underflows of balances or other accounting aspects related to such variables can and have resulted in critical vulnerabilities. These checks, until Solidity version 0.8.0, had to be implemented by the developer themselves, either within their own smart contracts or by using OpenZeppelin's Safe Math library, which provided various arithmetic library functions for addition, subtraction, multiplication, division, and so on, that implemented these checks in the library functions. Solidity recognized this aspect of arithmetic checks and how they're used all over in most of the smart contracts, because nearly every contract deals with such integers and therefore these checks. So as of Solidity version 0.8.0, Solidity language itself introduced arithmetic checks by default for integer types. Such checks are now implemented by default, and they can be overridden by the developer where you know that those checks are not necessary. So to sum it up, arithmetic checks are one of the most critical checks that one would encounter in Solidity contracts, and until version 0.8.0, you would see an extensive use of Safe Math library from OpenZeppelin for doing so, and from 0.8.0 onwards, these are implemented by default. So these three categories of checks that we talked about so far, the zero address checks, transaction origin checks, and arithmetic checks, are three categories that you would encounter often in the context of the concepts of Solidity that we have discussed until now. Let's now move on to the next topic of libraries that you would encounter almost in every smart contract that you would be looking at in Ethereum. Many, if not most, of these libraries are written and maintained by OpenZeppelin, which is one of the leaders in this space in not only in developing these libraries, but in security of Ethereum smart contract itself. They provide multiple services and multiple tools in this context. So these OpenZeppelin libraries are widely used. They have been time tested for several years now, and they've also been optimized over time with respect to the gas consumed by these libraries, and also with respect to the various Solidity versions that have been released over time. And one of the most common OpenZeppelin libraries that you would encounter is the Safe Math library that we discussed in the context of arithmetic checks. There are also numerous other OpenZeppelin libraries related to the implementation of token standards, various security functionalities, proxy contracts, and utilities. We would encounter one or more of these OpenZeppelin libraries when you're developing smart contracts as a developer, or when you're auditing smart contracts for their security. So for the remaining part of this module, we will be looking at 40 different OpenZeppelin libraries across all these functionalities. We won't be able to go into the details of each one of them, the various functions they implement, their nuances. As such, we will be touching upon some of their key aspects and talking about maybe the context in which they're used. As always, I would encourage you to look at the source code of these libraries and understand the nuances, the corner edge cases, any deprecated aspects of these libraries as they have changed over time, and the various variants of these libraries that should be used in different contexts because they affect the security of the contracts using them. Let's start with the OpenZeppelin library that implements ERC20 token standard. This is perhaps the most popular, widely used, commonly seen token standard that you would encounter as a developer or as a smart contract security auditor. This library implements all the required functions specified by the token standard. It implements the name, symbol, decimals. There is the total supply that returns the amount of tokens in existence so far, the balance of function that returns the amount of tokens owned by specific accounts, the transfer and transfer from functions that help move tokens from one address to another, the notion of allowance, which specifies a spender in addition to the owner of the tokens, where the owner grants a certain allowance to the spender, after which the spender can spend those tokens and send them to different other addresses. And in the context of allowance, there is the notion of increasing or decreasing allowance that the owner implements for a specific spender. There are various extensions and presets and utilities related to these standards, which we will talk about next. One such utility related to the ERC20 token standard is what is referred to as safe ERC20. The transfer from, approve, increase and decrease allowance functions of ERC20 tokens are expected by the specification to return a Boolean value. However, contracts implementing the standard might choose not to return a Boolean, deviate from the specification effectively. They may revert for these tokens on these functions under certain conditions, or they may return no value. And these differing return values or exception handling in the case of ERC20 tokens have resulted in security vulnerabilities. Therefore, this safe ERC20 utility implements wrappers for these functions. It implements the safe version, so safe transfer from, safe approve, safe increase and decrease allowance, that always revert on failure after checking the different conditions for these functions. And you may notice this utility being used with contracts with the using directive of Solidity as shown here. The next utility is what is known as token time lock. This implements a token holder contract where tokens are held by the contract. There's a specific address that is defined as the beneficiary address for all the tokens held by this contract, and that are only released to that beneficiary address after a particular time has expired. And the application for this, as you can imagine, are for things like token vesting, where a certain number of tokens are allocated to the various team members, to the advisors, and so on, that need to be claimable by them only after a certain point in time. So this library implements the notion of a token, the beneficiary address, and specifically a release function that, when triggered, checks if the block timestamp is greater than the release time that was declared earlier, and if so, transfers the amount of tokens held by the contract to the beneficiary address. The next one is the OpenZeppelin library that implements ERC721 token standard. This is the token standard that is commonly referred to as NFTs or non-fungible tokens. Perhaps the other widely used popular token standard besides ERC20 that we just talked about. Unlike ERC20 tokens, ERC721 tokens are considered as non-fungible because every token is distinguishable from the other. Every token has a token ID, and unlike ERC20 tokens that are indistinguishable from each other. So this library implements all the required functions as per the specification. There's a balance of function that returns the number of tokens in the specified owner address. There's an owner of function that returns the address that owns the specified token ID. There are the transfer from and safe transfer from functions that allow transferring tokens from one address to another address. The safe transfer from function makes certain checks before doing the transfer, and there are multiple requirements or checks implemented with respect to the zero address, with respect to the ownership of the tokens, and specifically to check if the recipient is a contract account, and if so, if that contract recipient is aware of the ERC721 protocol itself. And this is done to prevent these tokens from getting locked in that address forever. Approvals with ERC721 work differently from ERC20. Unlike ERC20 that has a notion of a spender for the tokens, ERC721 introduces the concept of an operator, which is somewhat similar. The approve function in this case specifies the address of the operator and the specific token ID, and it gives permission to the operator to transfer this particular token to another account. This approval is automatically cleared when the token is transferred, and only a single account can be approved at any time, which means that approving the zero address clears the previous approvals. There are other functions associated with the ERC721 as part of this library, and there are also various extensions, presets, and utilities similar to the ERC20 contract. The next library is one that implements the ERC777 token standard. This is a token standard similar to ERC20. It's backwards compatible with ERC20. So it implements a standard for fungible tokens and considered as implementing several improvements over ERC20. One of the key features is the notion of hooks, which are functions within the contract that are called automatically when tokens are being sent from it or when tokens are being received. This allows the contract to control and reject which tokens are being sent and which tokens are being received. These features allow us to implement several improvements over ERC20, such as avoiding the need for a separate approve and transfer from transactions, which is considered as a significant user experience challenge for ERC20 contracts. ERC777 also allows one to prevent tokens from getting stuck in the contracts using the hooks feature. This also implements the decimals as being a fixed value of 18, so there's no need for the contract to set or change it. It introduces the notion of operators that are special accounts that can transfer tokens on behalf of others, and it also implements a send function where if the recipient contract is not aware of ERC777 by not having registered itself as being aware, then transfers to that contract are disabled to prevent tokens from getting stuck in that contract. ERC1155 is another token standard that allows a contract to manage tokens in a fungibility agnostic and gas efficient manner. So a single contract that implements this standard can manage multiple tokens, some of which can be fungible tokens like ERC20 or non-fungible tokens, NFTs, and all these are managed within a single contract. This means that a single transaction can manipulate multiple tokens within that transaction. This makes it very convenient from a user experience perspective. It also makes this standard very gas efficient. And specifically, this standard provides two functions, balance of batch and safe batch transfer from, that allow querying balances of multiple tokens and transferring multiple tokens in the same transaction. So this makes the management of these tokens within the contract very simple and gas efficient. The ownable library of OpenZeppelin allows a smart contract to implement basic access control by introducing the notion of the owner for a particular contract. The default owner is the address that deployed the contract, and this allows the smart contract to implement access control on special or critical functions that modify critical parameters within that contract to only be accessible by this owner address. And this is made possible by the modifier only owner within this library. So by applying this modifier to functions that need to be accessed only by the owner address, this basic access control can be implemented. This library also supports the transferring of ownership, where a new owner can be specified to be switched over from the existing owner. There's also the renounce ownership, where the ownership is set to the zero address, which essentially makes all the only owner functions uncallable thereafter. OpenZeppelin provides a second library to implement a more flexible access control known as role-based access control, or RBAC for short. This allows a contract to define different roles that are mapped to different sets of permissions. And by using the only role modifier, different functions, access to different functions can be restricted to specific roles. Every role also has an associated admin with it that can grant and revoke those roles. So unlike Ownable, which implements a very basic access control using the notion of an owner address and all other addresses, this library allows for a more flexible role-based access control. The Pausable library from OpenZeppelin is interesting from a security perspective because it allows teams to execute what is known as a guarded launch. And what this means is that when the team is launching a new project with smart contracts, it's good for the team to anticipate potential emergencies that could arise, and using this functionality of the Pausable library, they can pause the smart contracts, deal with the emergency, remediate any risks from that emergency, and then unpause the contracts to continue normal operations. And this is made possible using the pause and unpause functions that can be triggered by authorized accounts. So these functions allow the authorized accounts to pause the contract and unpause it at the desired times. And the way this works is by using the when paused and when not paused modifiers on different functions. So on all functions that should be callable during the normal operations of the contract, the when not paused modifier should be used. And for those functions that should still be callable during emergencies, the when paused modifier should be used. So effectively, this library allows project teams to implement a circuit breaker mechanism to deal with any vulnerabilities discovered in the contracts, or to also deal with exploits that are happening with the contracts, when they can use the pause functionality, pause the contracts and all the user interactions with the contract, mitigate the risk from that emergency if possible, and then resume normal operations by unpausing the contract. The other OpenZeppelin library that is very critical to security is the Reentrancy Guard library. This is used to mitigate the risk from reentrancy vulnerabilities that are somewhat unique to smart contracts and very, very dangerous. This is the vulnerability category that was exploited during the DAO hack, which has historical significance to Ethereum. And what a reentrancy vulnerability is if our smart contract is making an external call to another contract, to any other function of an external contract, where that external contract is potentially untrusted, so it is not one of our own contracts and it's been deployed by some other project team, part of some other project, then in such cases, those external contracts can make a nested call to our contract, so they can re-enter our contract function, the function that made that external call or any other function. And in cases where certain contract state has not been updated within our contract, that aspect can be exploited by this nested call to do things such as transferring tokens multiple times, or triggering logic multiple times, where in fact it should have been able to do that only one time. So this at a high level is known as a reentrancy attack because of the concept of re-entering or nesting that happens, and that can be exploited in many different ways. So this particular library introduces a modifier called non-reentrant, and when this modifier is applied to different functions in our contract, those functions cannot be re-entered after making an external call. So this aspect can be used to mitigate reentrancy risk and is one of the standard security best practices that is recommended. And note that all these security features implemented in these different libraries, where specific modifiers need to be used for implementing those checks, all these aspects are applicable only on functions that use those modifiers. So just by using those libraries in those contracts, we do not get the security benefits. Those benefits are realized only on functions where this modifier is used in the expected manner. OpenZeppelin implements a pull payment library that is relevant in the context of payments. Payments between two contracts can be done either by the paying contract pushing the payment to the receiver account, or the receiving contract doing a pull of the payment from the paying contract. And this is interesting in the context of avoiding reentrancy attacks. So in the case of the pull payment library, the paying contract makes no calls on any of the functions of the receiver contract, because the receiver contract may be potentially malicious, and it's better for that receiving contract or account to withdraw the payment itself by using the notion of pull. So this prevents reentrancy by favoring the pull payment as opposed to the push payment, and therefore is standard security best practice that is recommended. The OpenZeppelin address library implements a set of functions related to the address type. The first one is the isContract function that we often encounter within different smart contracts. This takes an account address as a parameter and returns a boolean. This function returns true if the account address is a contract. However, if it returns false, then it is not safe to assume that the specified address is an externally owned account. And the reason for that is because isContract will return false in 4 different situations. 1, if it is an externally owned account. 2, if it is a contract account but that is in construction, so within the constructor of that contract account. 3, if it is an address where a contract will be created. And 4, if the address specified had a contract in it but was later destroyed. So for all these 4 cases, this function will return false, and an externally owned account is only one of the 4 reasons. So this is something where contracts using this function typically make incorrect assumptions about what this function does, and something that has to be paid attention from a security perspective. The second function is send value. Recall that Solidity has a transfer primitive that sends way to a recipient contract but limits the gas supplied to 2300 gas units. Now this has a drawback that if the cost of gas cost of certain opcodes increases over time, then the 2300 subsidy is not going to be sufficient for some of the logic that would be implemented within the fallback function of that contract. So the send value function removes this 2300 limitation and forwards all the available gas to the callee contract. This library further implements wrappers around the low-level call primitives supported by Solidity. So for call, static call, and delegate call primitives, there are equivalent wrappers that are considered as safer alternatives to using these low primitives directly. The OpenZeppelin arrays library implements array-related functions. There is a find upper bound function that takes in a UN256 array along with the UN256 element. The array is expected to be sorted in ascending order with no repeat elements in it, and it returns the first index in that array that contains a value greater or equal to the specified element. If there is no such index, which means that all the values in the array are strictly less than the element, then in those cases the length of the array itself is returned.